Now, I want to start a new topic today, and I'd say we'll be at it for about 3, maybe 4 weeks. So it'll take us up to uh, the midterm, really. And this topic called serverless. So I'm just going to introduce the topic first, and then we'll get into the AWS specific services under this serverless kind of heading. And you may have read a little bit about serverless already, and that's fine. So, but I'm going to take it from the ground up, really. So the first thing we always say about serverless is that it doesn't mean there aren't any servers within our infrastructure. There certainly are, but what it does mean is that we don't have to, as developers, we don't have to worry about the provisioning of servers. As developers, we can concentrate on developing our application code. We don't have to manage any part of the stack underneath our code, be that at the operating system level, third-party library level, or indeed hardware level. All of that provisioning is managed by the cloud provider, subject to some configuration settings that you give to the provider, and it takes care of actually provisioning all of that for you. And so pre-serverless, these are the kind of issues that I'm listing here that you would be concerned with, or you had to consider as a developer stroke operator. You know, how many servers, physical hardware servers do I need? How much capacity is left on my servers? Can I run other applications on them? Obviously hardware issues, but then on the operating system level, you were responsible for making sure that whatever operating systems you ran on your servers, that they were patched and up to date. You had to manage who had access to the servers, and so on and so forth. So all of those really important aspects are now taken out of your hands, admittedly. So you've lost that element of control. But the benefit, of course, is that you can now concentrate on developing your applications for your end users. And so what does serverless mean? I've kind of told you a lot of what it doesn't mean, but what it does mean is, well, we've already established point number one. There are no servers to provision or manage on our part. Point number two is that it scales with usage. So when we run our applications on top of a serverless infrastructure, then it will scale up and down automatically for us. That's part of the agreement that the cloud provider ensures. So the more traffic that hits your application, then it will scale up to deal with that high volume of traffic. And when the traffic goes down, then it'll scale back down again. So this is something that you would have discussed in DevOps last year. And so you had this application load balancer, and you define scaling groups and all this kind of stuff. So you, the developer stroke operator, were responsible for managing scaling there, whereas now that's again taken out of your hands and out of your control, admittedly, and taken care of by the serverless platform that you're building on top of. Point number three, also very important, pre-serverless, then, you know, when you stood up your EC2 instances and your application load balancers, irrespective of whether there was any traffic hitting them or not, or the volume of traffic, you were still paying for the fact that the servers were up and running. Whereas in the serverless model, you only pay for the amount of traffic that is actually hitting your application. So you're paying for the value that the serverless platform is providing to you. So it's a pay per usage kind of model. Point number 4, availability and fault tolerance. That's built in to the serverless platform. So you're guaranteed the infrastructure is always going to be available and it's fault tolerant. Again, that's taken care of by the infrastructure provider for you through replication and other means. The benefits then, I guess, are fairly obvious. If you no longer have all of these other responsibilities that I'm talking about, if they're taken away from you, then you can now focus on developing business logic. I'm saying number 1, you've got greater agility. Your application can scale up and scale down easily. You have less overheads. That's on the pay side, because you're no longer paying for potentially EC2 instances that are over provisioned and they're not being used constantly. On point number 3, increased scalability. I've already talked about that. And point number 4, you better focus on, you can focus on the developing of the application itself rather than worrying about what lies underneath the application. And the final point, faster time to market. Well, if your only concern is developing the functionality of your applications, then you can get that to market quicker than if you had to worry about all of the other lower parts of the software and hardware stack as well. So it's very much a developer kind of focused idea, this serverless idea. And as would have been mentioned before to you, you're relinquishing control, okay, to the cloud provider, but the benefits are you can focus more on developing your applications. Now, turning to AWS then, because obviously all of the cloud providers at this stage now have a serverless offering. And in terms of AWS, it has many services which are categorized as serverless. And I'm mentioning some of them here, and we won't get through all of them, but we will get to look at some of them. And so you may have heard of these along the way, taking it from the top down. AWS Lambda, which I'll talk about today, that's your serverless compute, one of the serverless compute options available to you. And as I would have mentioned now on a number of occasions, we no longer require EC2 as our compute service. We're now going to be using, from here on in, we're going to be using Lambda as our compute service. DynamoDB is just a non-relational serverless database, which we will look at. We're not going to spend a whole lot of time on it. I'll just give you the basics of DynamoDB. I mean, this module is not really a database module, so but in terms of the serverless idea, it would be front and center of AWS's serverless data persistence offering. AWS Cognito is a service for managing your users. So, user accounts, credentials, all of that. Well, yeah, credentials in terms of just passwords. These are users now of your application as opposed to users of the infrastructure itself. So this Cognito service takes care of all of that stuff that you would have programmed last year in the web app dev module. If you remember, you would have a users table and you had to manage user accounts, essentially passwords and all of that kind of stuff. Now AWS Cognito will do all of that for us, and we'll have a look at that in a while. API Gateway is a serverless service for front-ending any REST or web APIs that you might develop, and we'll certainly look at that service. API Gateway is very like the application load balancer idea, but of course, application load balancer is not serverless. whereas API Gateway is, but it has a lot of commonality to the idea behind of an application load balancer. S3, of course, you've heard of. It's our storage service, but it's essentially serverless, even though it predates the serverless idea. SNS and SQS are what I'm calling messaging services. Don't know if you've come across these at all. Probably not. We will look at both of them, albeit at the back end of this module. It'll be quite a while before we get to look at it. But essentially, SNS stands for Simple Notification Service. SQS stands for Simple Queuing Service. These services allow you to integrate different parts of your application. So if you've got one piece of functionality that wants to communicate with another piece of functionality, but not directly, kind of indirectly, you can use these messaging services as intermediaries. And we will be doing that, but as I said, not until the latter end of this module. Now, everything that I've mentioned so far, we will come across in this module. The other ones that I'm mentioning here are just, I'm just mentioning them, but we won't get around to using them. So AWS Kinesis is a data streaming platform. We won't get to go near that. Aurora is also a database service. It's a relational database service. But the nice thing about it is that it's a serverless relational database service. Bit of a mouthful. Step functions are a way of essentially defining a workflow between a group of Lambda functions. Again, we won't get around to it. Fargate is a serverless container service, and there are lots more of them. So there's plenty of serverless services there. On the right, what I'm showing you there, that diagram, is essentially it's a serverless approach towards developing a web application. So last year, he developed a web application. He developed the front end and the back end. Now, some of you may have deployed it, but you would have deployed it onto a server-based platform. Whereas with a serverless model, the way it would work is we would use S3 to host our React app, our front end. You can actually use S3 as a website hosting service, as well as just being an ordinary storage service. And then the rest, all of this stuff here is essentially your web API side. Yeah. And what I've enclosed there now in that red is something that we will actually develop. So the API gateway is this serverless service, and it's kind of a front end for your REST API. So all the HTTP requests would be handled by this API gateway service. And you'd have a number of Lambda instances, and the API gateway would route the request to the appropriate Lambda. So you can imagine now you have a number of Lambdas strung across here. And each Lambda deals with one part of your web API's backend. And down to the very bottom, we have a database, and we would be, because we want to follow this serverless model, we would use, potentially anyway, DynamoDB as our database. And all of the Lambdas that are lined across here, all of them have the option of talking to this DynamoDB database. On the right then, I'm suggesting we're going to use we're going to use Cognito for just managing user accounts. Yeah. So, if we have the web app dev module following on from this module, then we could certainly use this infrastructure as the deployment platform for our web API that you would have developed last year. Now, in this module, we will look at this part. Okay, we won't look at the idea of S3 hosting a front end. We're not concerned with front end at all in this module. Anyway, that's all ahead of us. All I'm getting across in this picture here is this idea that what serverless has enabled is it has allowed the developer, and I've mentioned this once or twice already, it's allowed the developer to focus completely on developing functionality. And so the kind of diagram shows you how things have evolved over the years. Like in the earlier days, all we had as developers available to us might have been just the hardware itself, and we had to deal with, all of the software stack on top of that and managing all of that as well as developing the application. Then we moved into the VM kind of era, virtualization era, where we no longer were as concerned about the low-level hardware. Then we moved into the containerized era. Don't know if you've done anything on containers anywhere along your studies, but a container is essentially runs on top of a VM, and a container includes your functionality as well as the operating system, etc. Now we're in the era where a developer is only concerned with just developing functions, and everything else is taken care of by the underlying cloud provider. So we've gone from just worrying about everything essentially, or being responsible for everything, to now only being responsible and concerned with just writing our application code. No concern with operating system, which you didn't have to concern yourself with here. You did to a degree here, and certainly here. So, there's decreased responsibility, but also a certain lack of control. But the gain is that you've got more time to spend on developing functionality. Right, so that's just by way of an overview of serverless. Let's dig into some specifics. So what I'm going to do over the next few weeks is look at a number of AWS's serverless services. I'm going to look at Lambda. I'm going to look at API Gateway, DynamoDB, Cognito. I think I'll cover those 4. And then we will have enough knowledge. If I just go back, we'll have enough knowledge to be able to develop something like what's enclosed here in red. Essentially, to develop a serverless backend or web API. We were not, as I said before, we're not really concerned about the front end side of it. So that's the kind of objective down the line. So what is Lambda? I'm saying Lambda is an event-driven serverless computing platform. Kind of already given an indication that it's got to deal with computing or compute. The event-driven is important. So if I've got some functionality that's running on the Lambda service, how do I actually trigger the execution of that functionality? Where I'm saying here that it's very much event-driven. So you have to associate, and you do this in your kind of configuration, you associate some type of event, and on the occurrence of that event, your Lambda function gets invoked. The AWS platform will take care of invoking the Lambda for you. You've just got to tell it what event will potentially trigger the execution of the Lambda. So it's event-driven as opposed to user directly driven, I suppose, let's say. I'm saying it's a computing service that runs, it just runs code. You just give it code. That's all you have to provide, and it takes care of the rest. And you give it code just in the form of a function. Okay, and the AWS service, in conjunction with AWS itself, it takes care of provisioning whatever resources that code needs in terms of what RAM does it need, what CPU power, how much CPU power does it need, what networking services does it require? The platform will take care of all of that. Essentially, what happens is you provide a function to the AWS Lambda service. You tell it what type of stack you'd like that function to run on in terms of the operating system that you want, the hardware potentially, how much CPU power, how much RAM, how much networking, and that's your kind of configuration. And the AWS will take care of provisioning all of that for you, and it will run your code. And it runs it inside what's called a micro VM. So it provisions a micro virtual machine environment for your code to run, where that micro VM contains a particular configuration based on instructions that you've provided. I'm saying here the quote is that it's a custom code that runs in an ephemeral container. Ephemeral means that the container is just created on the fly whenever, I said a few moments ago, that the triggering of the execution of your function is based on the occurrence of some event within the cloud. When that event occurs, the occurrence of the event will cause the AWS Lambda service to essentially instantiate a micro VM container for your code. It will load your code into that container. It will run the code. And then when the code is exited, it will essentially throw away the container until the next occurrence of that event. So this idea of creating and destroying the containers in that way, now, in some circumstances, it will actually hold on to the container just in case there is another occurrence of the event in the immediate future. So it just doesn't throw it away immediately. It does hold on to it for a little bit, just in case there's a second occurrence of the event. And if there is, then it reuses the container that it has just created. But if there are no subsequent occurrences of the event in the short term, then it will just throw away the container or the micro VM. Another expression we use is that this is all about FaaS, function as a service. You probably heard of infrastructure as a service, platform as a service, software as a service. Well, the next generation, the current generation that we're in, is in this function as a service era. Function as a service and serverless are kind of interchangeable, although FaaS just refers to the compute aspect of serverless. So the graphic is kind of reiterating the first point on the previous slide. So this is the Lambda logo, as you probably know. So this is representing the code, the function that I've provided to the Lambda service. And there has to be some event to occur that will trigger the execution of my Lambda. Now, we refer to this as the event source for my Lambda. And the event source, typical types of event sources, the one that you might expect is a HTTP request, the arrival of a HTTP request to the AWS cloud that will trigger the execution of your Lambda function. Another possibility is you can actually link changes to any data storage infrastructure that you might have. You can link changes to the state of the data storage to the triggering of a Lambda function. For example, you might have a database, and whenever there is a new record added to the database, you want to trigger the execution of your Lambda on the occurrence of that. So the record has been put into the database, and that is what triggers the Lambda to execute, as opposed to the Lambda, first of all, putting the record into the database. There may be another Lambda that's responsible for adding a record to the database, but on the occurrence of on the event of a new record being put into the database, that could also be the source for triggering or executing another Lambda function. Equally, if you're using S3 as part of an application's infrastructure, maybe you want a Lambda function to be executed whenever something happens to an S3 bucket, like a new object is added or an object is updated within an S3 bucket. They could also be potential event sources or triggers for the execution of a Lambda function. And indeed, any service that experiences a sort of a state change, this is what I'm making in point number 3 here. Any service that experiences a state change, you could associate that state change with the triggering or the execution of one of your Lambda functions. Simple example might be, you might even have an EC2 instance. And if that EC2 instance, let's say, goes down, that's a state change. You can link that event with the execution of a Lambda function. Now, we certainly won't be doing that. We will be see how to achieve 1 and 2, okay, but we won't be concerned with option 3. So the overall point is a Lambda function is executed as a result of some event occurring within the infrastructure, and you link the event type to the Lambda function. That's what you do in terms of your configuration, and the rest is taken care of by the Lambda service itself. In the middle here, I'm saying that your Lambda function, you can write it in any language you want to. Well, pretty much anyway. And in terms of what the Lambda does, the Lambda can do anything. It can talk to any other service. It can talk to DynamoDB, it can talk to S3, it can talk to SQS, etc., etc. So it can do pretty much anything you want it to. So the Lambda service, so we talk about the Lambda service and our Lambda function. The Lambda function is what we write and we deploy it to the Lambda service itself. So the Lambda service I'm seeing here, it handles auto scaling. Now, if I just go back to the previous slide, so I've got this Lambda function and I'm associating it with a particular event source. Now, let's supposing we've got multiple occurrences of that event happening concurrently. What actually happens is the Lambda service will create multiple instances of your Lambda function, or more specifically, it'll create multiple instances of the container that I talked about on the previous slide, the micro VM. It'll create multiple instances of that container, load each container with a copy of your Lambda function code. And so that's how scaling simply works. If you've got concurrent events happening and there's a particular Lambda function that needs to be executed as a result of that event, then the AWS Lambda service will just spin up a number of micro VMs to run copies of your code. So it's, in other words, it's kind of horizontal scaling. And as each instance of that micro VM completes the handling of the event, then either the Lambda service will throw away that micro VM, or it will more than likely leave it there for a short while, just in case there are more occurrences of the event following on. And it'll just route the events to any of the spare micro VMs that happen to be still available to it. So it does auto scaling. It does load balancing, so I'm just kind of talking about that there really. So it might have, let's say, 5 instances of a micro VM container containing your Lambda code currently available to it, because there were 5 concurrent instances of the event in the recent past. Another instances of the event arises, and the AWS Lambda service will just route that event to one of the available micro VMs that is available to it. So it load balances between all of the potential multiple instances of these micro VM containers. It manages the operating system side for that micro VM. It manages the security. By security, I mean potentially the micro VMs might all be running on the same physical hardware, but obviously each micro VM is isolated from every other one. So it will guarantee that. That's what I mean by security isolation there. It also manages any of the utilities that a micro VM might need. And by utilities, I mean how much RAM does it need? What CPU, virtual CPU power does it require? What networking does it require? That's all really dictated by the configuration of the Lambda that's running inside the micro VM. And you provide that configuration information. So the Lambda service does all of that for you. That's typical of this kind of serverless idea. Takes care of scaling, balancing, operating system management, security, managing the actual physical resources that are required. When we're talking about compute, serverless compute now. On the right, then I'm talking about characteristics of this whole serverless compute idea, which is what we're focusing on right now. So the first point I'm saying is that what we're talking about here is functions as a unit of scale. You see, pre-serverless, okay, you develop an application and you deploy that application, let's say, into an EC2 instance. If you want to scale up that application, you have multiple EC2 instances, each running the full application. But it may only be part of the application that needs to be scaled up, because there's only one particular part of the application that's receiving high volumes of traffic. But in the pre-serverless days, you had to scale up multiple copies of the entire application. Whereas in the serverless model, we're talking about that it's only particular functions within our application that are experiencing high volumes of traffic. And so it's only those particular Lambda functions that we need to scale up, or that the infrastructure needs to scale up. In other words, create multiple micro VM containers, copies for that particular function or subset of functions. So you can scale at a much more granular level than you could pre the serverless idea. A function is now our unit of deployment. Previously, when we developed an application, we packaged it in some way and we deployed the entire application as one entity. If you wanted to make a modification to a part of the application, you still had to rebuild the entire application and redeploy the entire application. Now, what we can do is do our redeployment down at a more granular level, at the function level, because each Lambda is completely independent of every other Lambda that make up your entire application, each Lambda function. The statelessness nature, well, I mentioned there that, okay, our Lambda function now is going to run inside a container, which is running inside this micro VM instance. And I said that whole infrastructure is ephemeral, means it just can be thrown away once the function is finished executing. So there's no sense that you can pass data between one invocation of your function and the next one. That's what we mean by statelessness. There's no memory within your Lambda function. There's no memory of when it ran previously. So that affects your programming model. That would not have been the case in the pre-serverless days. Also, you know, there is a limit as to how much functionality you can put into a Lambda function, and it's limited by the time it takes for the Lambda to execute. So I think the maximum amount of time that a Lambda can continue its execution is for 15 minutes. So if whatever type of processing you need to do requires more than that, then you shouldn't use a Lambda function as a way of implementing that particular piece of functionality. So it's limited by time. And well, runs on demand. I've already kind of made that point. Your Lambda function is loaded into a VM, a micro VM container only when it's needed. Other than that, it's just stored. The function is just stored in memory, in long-term memory now, not RAM. Pay per request. I've also mentioned that point. Right, you only as the customer, as the AWS customer, you only pay for the amount of times your Lambda function gets executed, and there is a fairly generous free tier offering in the Lambda service. You don't pay for any idle time, which was one of the problems with the EC2 model. You did pay for idle time. Right. Eventually, we get to see some, getting a little bit closer to seeing some code. So I want to write a Lambda function, and it is literally a function in the every sense of the term from a programming point of view. So in the screenshot here, here is, let's say, my Lambda function. It doesn't have to be called handler, but we refer to the function as the handler. Okay, so this is where I put the whatever processing I wanted to have carried out within this function, and it has to be exported, and it has to be asynchronous, because of course this is running across a network always. The physical file that contains your Lambda function, it can have other functions for sure, but those functions are just private. So presumably if I have other functions here, they're being invoked by my handler. The handler is essentially kind of your entry point in from the Lambda services point of view, and that's where execution centers on. Now, there's also a part of your code which is referred to as the initialization part of your code, and that has to be outside the handler. And in the initialization part of your Lambda is where you put, well, any initialization code, which, for example, might be if you want to create a database connection, then put that code outside the handler. You can put it inside the handler as well, but that's just bad practice. Put it outside. So the handler is the function that gets executed upon occurrence of when your Lambda is invoked. The event object that triggers the execution of your Lambda, that event, presumably you want to process it within the Lambda itself. So the event object is made available to your handler as the first argument, as we can see here. Sorry, here. And there is a second argument, which I haven't really used that much. It's the context. So you can access the execution environment if you need to within the handler. Now, so when I was talking there about, so an event occurs, and that event, let's say, is linked to this particular Lambda function. The the Lambda service will create a micro VM instance, and it will provision it with the relevant operating system and RAM and CPU power that's required. And then what it will do is, in terms of executing your Lambda function, it will first of all execute the initialization code, and then it'll execute the handler. And when the handler has finished, that's its job done. Now, it doesn't, as I was saying there earlier, it doesn't throw away the micro VM instance that it has created immediately. It holds on to it for a little while in case there is another occurrence of the event. And let's supposing there is a second occurrence of the event in the short-term future. Now, when that event arises, in this case, the initialization code is not executed because we still have whatever initialization we had to do here, we still have that available to us. In this, it's only going to execute the handler in the second instance of the event. So there's that kind of benefit, right? It doesn't need to re-execute the initialization code every time, but that's only if it's using a micro VM instance that it had already provisioned for an earlier occurrence of the event. Now, we're talking about seconds, really, between the first and second event, admittedly. The first time it runs everything, when it has to run the initialization code and the handler, we refer to that as a cold start occurrence of our function execution. The second occurrence, where it doesn't need to run the initialization code because it still has the various connections or whatever was done inside here, it still has those because the micro VM hasn't been thrown away yet. The second instance is referred to as a warm start, and in a warm start, it essentially skips over this and then just runs the handler itself. And so there's obviously, from a latency point of view, there's a big difference between a cold start invocation of a Lambda function and a warm start invocation of a Lambda function. And that can be significant for large-scale applications where latency is a major issue. Okay. From a Lambda configuration point of view, and in terms of how many kind of dials are available to you to control the configuration, and by configuration, we were mainly talking about the level of compute power that you need or that is required by the Lambda function itself, depending on what it does. You know, if it's doing heavy video processing versus basic number crunching, obviously it needs more compute power in the video processing example. Now, the AWS themselves, what they decided was that the only control that it gave to you, the developer, was to indicate how much RAM space your Lambda function required. Now, we're not going to get into how you compute the relevant RAM space for Lambdas in this module, but I'm just making you aware that the only thing you can configure in terms of compute power is how much RAM your Lambda needs. And the Lambda service then uses that to determine how much virtual CPU power it should provide to the container that it instantiates for you, and also what kind of networking bandwidth it makes available to that container instance. So essentially the AWS people have made our job a little bit easier in the sense that we need to only think about the amount of RAM space that we'd like to have available to our Lambda function. And the AWS Lambda service then takes care of everything else, takes care of provisioning it with the appropriate virtual CPU power and the networking bandwidth. And I'm giving you some facts and figures here. Okay, so the smallest amount of RAM space that you can specify is 128 megabytes, and the largest is 3000 megs, and it jumps up in blocks of 64. The more RAM, as I've said, the more RAM you add, then the more virtual CPU credits that are allocated to the micro VM that's instantiated to run your code. And that's okay. There's also something that you can also configure is the timeout allocation for your Lambda function. Now the default is 3 seconds. So in other words, if your Lambda does not complete its execution in the timeout period, then by default, it's assumed that the Lambda has crashed and throws an exception. Now, there are different ways of dealing with that, but so again, you can also control the timeout limit. So again, that's something you would have to kind of compute or measure, but equally, we're not going to get into that. So timeout and RAM are the only two dials, if you like, that we can control, and they are sufficient to allow the AWS platform to take care of provisioning your micro VM accordingly. So to demonstrate the kind of hello world of all of this, and we're going to do everything through the CDK, obviously. That's why we looked at it up to now. So if I flick over to my VS Code, here I've got a CDK project, and in the actual stack itself part, then really the only part of my stack is just this. So this is how we provision a Lambda function for my application. My application, it just consists of this Lambda and nothing else. In terms of the imports, it's the same as before. I mean, I didn't look at the CDK, or I didn't talk about the CDK library tree, but it's broken up into a number of packages. And so it looks like this is the package here that we can use, the part of the CDK package that we can use if we want to create a Lambda function, and specifically a Lambda function that's running on Node. Okay, so it's very focused in that sense. We know that we can implement our Lambdas in lots of different languages, but if we're implementing it in TypeScript / JavaScript, then this is the library to use. And there's another part of the AWS library that I'm using here as well. And so to instantiate or to provision a Lambda function that's going to run on top of the Node platform, this is how I do it here. A bit like in last week's stack now. So I'm going to create a Lambda function. I have to associate the Lambda function with a stack. That's what this argument is doing. This is just giving the Lambda function some sort of an identifier within my stack. And the rest then is the configuration settings that I want for that Lambda function. And some of these are actually optional. I didn't have to specify them, but I'm just including them. So obviously this one is dictating the hardware architecture that I want to run my Lambda on. Now, there is no particular reason why I wanted to run on ARM64, but it's there for illustration purposes. I'm specifying the runtime environment to be specifically Node version 16. And, if I just confirm now that the Lambda can be written in lots of different languages, you can see the kind of options that I have available to me here. could write it in .NET, in Go, in Java, and so on and so forth. But in this case, I want to run it on top of the Node platform, and specifically Node version 16. No particular reason why I picked version 16. I could have picked 18 because it supports that as well. It doesn't go any higher than that though. The entry property is where you specify where exactly is the implementation of my Lambda function. And in my case, the Lambda function is going to be inside in this folder here, which we'll look at in a second. I've just arbitrarily decided that the timeout is 10 seconds, which is way over what I need because my Lambda function doesn't really do anything significant. But that's how you control the runtime. And the runtime, setting the runtime to 10 seconds means that if for whatever reason on an execution of my Lambda, it doesn't complete its processing in 10 seconds, then it will automatically cause the Lambda to throw an exception. And what the client then has to deal with whatever that exception is. So that is my stack. Let's deploy that stack in the usual way. So my application is just comprised of one function. So if I flip over to the management console, there's my stack there. Now, I didn't show you the actual Lambda implementation though. All I've shown you is the provisioning of a Lambda instance up in the cloud, but the actual function itself, I've implemented it in here. And, it is the hello world. So here's my handler. I don't have any initialization code in this case. You don't have to call the handler. You can call it anything you want to, but it seems to be a convention anyway. And so this is a function just in the ordinary TypeScript sense. The function type is handler, which is just a type that I'm importing provided by the AWS Lambda SDK itself. There isn't much terribly interesting in to look at them. We don't need to look at the detail of this type, to be quite honest. It's pretty straightforward. It's an asynchronous function. Now, I'm not actually doing anything with the event or the context. All I'm doing in the body of my Lambda is just a console.log, and I'm returning this as the response from my Lambda to whoever is invoking it. So pretty uninteresting, other than we need to work out where do these console.logs go to. So that's my Lambda. I didn't have to wrap it in a try-catch block. That's a little bit overkill, but because there's nothing inside here that can throw an exception really, because the only thing that's the code that's executed within the Lambda is console.log, and that's not going to throw an exception. But it's again, it's conventional to wrap your Lambda in a try-catch block just in case there's any code within here that can potentially throw an exception. Okay, so that's that. Let's go back to here. And if I now bring up the Lambda service, and probably haven't used the service before, but click on functions here, we can see all of the functions that I have deployed in my account, all the Lambda functions, and surprise, surprise, there's only one. sorry, functions. And here's my function. Now the function's identifier, if you like, or name as it's calling it here, is just a concatenation of the stack that the function belongs to. The function name itself, which I controlled within my CDK code, and then just a randomly generated hash value. And if I click on that, it'll take me into the function itself and the configuration of it. Now, in terms of if I wanted to see the code associated with my function, then here it is here. Of course, I've written my Lambda function in TypeScript, and that has to be compiled down into JavaScript. And that's what we're seeing here, the compiled version of my Lambda. So there's quite a lot of wrapper code around it, but we don't have to study that at all. The whole point is that we stay within our TypeScript implementation and don't worry about the compilation of it down into JavaScript. That's all taken care of behind the scenes by a package called ESBuild, which is kind of built into the AWS Lambda CDK environment, if you like. Now, how do I actually invoke this Lambda? Now, this is kind of the exceptional case in the sense that, or the kind of the edge case, in the sense that I don't really have any event source associated with my Lambda. There's nothing in the CDK code that I wrote that indicates what are the potential event sources that would trigger this Lambda. So it's very much a standalone Lambda, but I can still invoke it. And there are a couple of ways I can invoke it from the command line using the AWS CLI. So let's just do that. So the first thing I might do is just use the AWS CLI to find out what Lambda functions are in this particular region for this particular account. Now, I don't need all of that because I'm going to use my default profile. So if I just get rid of, and I don't need the region either because my default region is EU West 1. Now the response that comes back is from the response comes back from AWS, from the Lambda service, is a list of all of the functions that are in my default region, EUS1, and there's only one, as we can see, and that's the function's name. Now, if I want to invoke that, I can again use the AWS CLI to do that using this format here. I don't actually need, because I'm not passing any data to this Lambda function, I actually don't need this stuff. I don't need this. I'm just showing you how you might pass a JSON structure to a Lambda function if you want to invoke it from the command line. But in this case, we don't really need that. So I'm just going to make a copy of that and take out the bits I don't need. Now, admittedly, this is hello world stuff, so it's fairly trivial in that sense, but and I need to give the function's name, the name that it has up in the Lambda service itself, which is this name here. So what I was talking there about the event source and all of that associated with lambdas. We're kind of bypassing all of that here now because we don't have a nominated event source for this lambda. So that's why I'm invoking it using the AWS CLI. Any lambda can be invoked using the AWS CLI, but so it's the only option available to me. So if I issue that command, now to explain, although it's fairly obvious, I suppose, I'm invoking this particular lambda from within my default profile. So that's automatically going to go to EU West 1 and my account. And the response is going to be stored in a local JSON file called response.json. So if I now hit return down here, now I do happen to have a response.json there, but maybe I'll just delete that before I issue the command. And if I now issue it, and if I look inside the response, so the status 200 tells me, well, the Lambda did execute, the Lambda function did execute successfully, but in terms of what did it actually return back to me, and what it returned back to me, hopefully is this data structure here. Okay, it's hard coded, but that's fine. So if I look inside the response.json, then that is essentially what I'm getting. So I have demonstrated triggering a Lambda just using the AWS CLI. The only thing left though is inside my Lambda, I have a console.log. So the question is where does that go to? Where does it output to? Any console.logs that you have in a Lambda, they will be sent to the AWS CloudWatch logs service. Lots of services use CloudWatch logs for outputting. And this is also the case with the AWS Lambda service. So I now need to go to CloudWatch logs. And this is something that you will be doing quite a lot because certainly in terms of debugging your Lambdas, you'll be using CloudWatch logs to try and find out why things aren't happening the way you expect them to be in your Lambda functions. So now CloudWatch is a service that you would have used last year in terms of the logs side of it. If you go into the way CloudWatch logs works is the CloudWatch service creates a log group for each service, each resource that uses it. In my case, my resource is an AWS Lambda function. The log group, it gives the log group for that resource, it gives it a name, and it's a structured name. So in the case where the resource is an AWS Lambda function, then the log group name is /AWS/Lambda, and then the rest is the specifics of your Lambda function. Because my stack was called simple stack, function was called simple function. This is the actual log group that the CloudWatch logs created for my Lambda function. And if I click on that, a log group contains log streams within it. So every time my Lambda function executes, the CloudWatch logs will create a stream within the log group for that invocation. And any console logs within my Lambda function will be put into that stream. And so I've executed the function once, and so there is a stream down here. And the streams are time-stamped. If you've got a number of consecutive executions of your Lambda, then it will more likely pack those into one stream rather than having separate streams for them. But anyway, if I click on that stream, and this is what a stream looks like. And here's the, let's see. Here's the start of the stream. This is the body of the stream, and this is the end of the stream. Now in the body, because I had only one console.log statement, if I expand this, then this bit here, that is what my console.log outputted. So that is aligned with the console log statement in my code. Yeah. Okay, so that's the kind of 101 of Lambdas. Really ordinary stuff though, but it's got to start somewhere, I guess. Okay, so I've invoked it. I've created my Lambda function via the CDK. I've invoked it using the CLI, and I've shown you where any console logs go to. Now, the title here is Lambda integration, but I'm not talking about integration here in terms of what your Lambda can do, because your Lambda function can communicate with any other AWS service. By Lambda integration here, I mean what services can trigger the execution of your Lambda. And this goes back to the kind of event sourcing idea, which the demonstration that I've just given you there doesn't have any illustration of event sourcing though. So it turns out that quite a number of the AWS services can potentially be the source of the events that trigger the execution of a Lambda function. And we'll see some of them in the next few weeks. Well, one in particular, I suppose, and we'll see others later on in this module. So I'm not going to go through the services that I mentioned here. Just suffice it to say that all of the services that I've mentioned here, some of them you're not familiar with, some of them you are. If you just take S3, for example, you can trigger the execution of a Lambda as a result of some state change in an S3 bucket. And I've kind of mentioned that already. But you've got to express that in your CDK code. And the CDK framework will take care of setting up the infrastructure to achieve that. So there's quite a number of services that can be the triggers for a Lambda function. The way it's modeled from a kind of an implementation point of view is you can have synchronous invocation of your Lambda function, an asynchronous invocation, or you can have what's called a polled-based invocation of your Lambda function. So there's three different models, and the various services that I'm mentioning up here, they are restricted to using one of the models, and this is all kind of prescribed by AWS. You can't do an alternative. So whichever service that you're using, you're using as the trigger for your Lambda function, you've got to look at that service's integration with Lambda and follow the particular programming model prescribed, whether that be synchronous, asynchronous, or poll-based. I'm going to talk about each of those briefly. We'll experience synchronous in the next week or two, and we'll experience the asynchronous and poll-based integration further down the line. So for the synchronous, which is usually the more straightforward kind of model, really, for a synchronous invocation, the services that follow that model are, well, if you invoke it from the CLI, which I've just done, so we were essentially using the We're invoking the Lambda function, and the CLI waited until the Lambda executed and responded back. That's typical synchronous invocation. Also, if you want to write an application that's using an SDK, so for example, you could write a Python script or indeed a TypeScript script, run that TypeScript locally on your machine, and use the SDK to communicate with a Lambda function. But the communication is synchronous as well, because the particular application that you have written is going to wait for the response. API Gateway follows this synchronous model. We'll look at API Gateway next week, I think. You can actually link up a load balancer with a Lambda function. Doesn't always, Lambda load balancer isn't always the front for an EC2. So we won't be looking at that, but that is possible. But if you do integrate a load balancer with a Lambda function, the communication between the two is synchronous. And there's also something called function URLs, which I'll illustrate in a minute to you. You can actually get the Lambda service to generate a URL for your Lambda function, and then you can invoke it from a browser or some other type of web client. But the communication is synchronous as well. And, you know, the picture here kind of demonstrates some of those. So if we're using the AWS CLI or the CDK, and we saw that there a moment ago, you invoke it, the Lambda executes and it responds back. If we're using API Gateway, which we will be doing next week, API Gateway is this serverless service for developing web APIs. But either way, your client, presumably your browser, sends a HTTP request to this API Gateway service. It communicates with the Lambda, and you have to, in the CDK code, you have to kind of set up this integration here. The Lambda executes, the response comes back, and the response is sent back to the client. But again, it's all synchronous. In the function URLs idea, you can actually invoke directly from a web client. You don't have to go through the API Gateway. You can have a web client that communicates directly with a Lambda if that Lambda function has a URL generated for it. So that's synchronous invocation. And let's see an example of that happening. And this example, I'm going to use the same CDK application that I had there a moment ago, my single little Lambda, but I'm going to get the CDK to generate a URL for that Lambda, and that will allow me to invoke it from a browser or from Postman. In addition, you can actually configure the URL to be a private URL. And in that case, there has to be some form of authentication with the HTTP request to the Lambda function. So how do I get the CDK to generate a URL from my Lambda function? So I'm just going to, because I've prepared this earlier on, I'm going to check out, did I make any changes there? No, I'm going to check out this branch. Again, let's look at the CDK code. The Lambda itself hasn't changed. I don't think it's much the same as before. The CDK code. Okay, I create my Lambda instance as before, and this is how I just get it to generate a URL for me for the Lambda. And so I'm adding a add a function URL. That's okay. You can configure the URL to be public or private. Let's start off by making it public. So the authentication type would be none in this case. And you can also configure a CORS setting for our CORS configuration for your URL if you want to, but I'm not going to in this case. And I'm also getting my CDK stack to output the generated URL for me so that I can then just use it. So that's my stack. Let's redeploy. Okay, and let's see, here's the URL. So this line here, that was generated. Not sure if I used this in last week's stack or not, but if that was generated by this line of code. Sometimes you want your CDK stack to output stuff to the terminal. And in this case, I'm asking it to output what I'm asking it to output. I'm asking it to output the URL associated with, the URL associated with this Lambda function. Is that how I'm, sorry, let me just check that now again. Okay, well, this simple function URL is some sort of a structure returned by this method. And obviously that looks like that structure, that object structure, contains within a property called URL. And that contains the URL that's generated for me. So anyway, I'm outputting that here. And so when I look at my terminal output, I can see it there. Where's it going to? There, sorry. So if I just click on it, then voila, I get my response. This is the response that was actually generated by my Lambda function. And let's confirm that that is still what the Lambda function generates. Yeah, it's the same. That's the, see, there's the text message that it generates, and that's what I get back in my browser. That looks good. If I now, let's say I want to make that URL. So I am triggering, what am I doing there? I'm triggering the Lambda via a URL that has been generated for it by the Lambda service. That ability to associate a URL with a Lambda, that's a fairly recent feature that was added to the AWS Lambda service. It's only been around since 2022, I think. Now, you can actually make that URL protected or private. And the only form of authentication that's supported for private Lambda URLs is based on the IAM based on the IAM's authentication. In other words, SIG-v4, if you're familiar with SIG-v4 from last year. So to make my URL private, I need to just change the configuration slightly of the stack. As in here. You can see there are only two options available to me, either public or private based on the AWS IAM authentication model. Let's save that, redeploy. So it's all pretty straightforward so far, really. I think there's nothing too much too interesting happening. When we start getting into bringing a database into the equation and API gateway, then we'll have a richer, we'll have a set of Lambdas all sort of sitting behind an API gateway, and that will provide obviously more functionality. And we'll just get the Lambdas, most of them just interacting with a DynamoDB database. So again, it's fairly standard kind of stuff, admittedly. The theme, though, is it's all based on this kind of serverless model. So here's my URL in this case. But clicking on it now isn't going to work because it's a protected URL, but let's try it anyway. Okay, so I get a forbidden. So now I'm going to switch over and use Postman as a way of invoking this URL. And in my, so I'm going to set up a GET request, HTTP GET request to this particular URL, but I need to provide my AWS access key credentials, and Postman takes care of using those credentials to generate the relevant authentication headers and indeed some query string arguments, generating all of those and sending them with the GET request to the URL to the AWS Lambda service. The Lambda service checks the authentication credentials that have been passed to it, and then it will either allow it to execute the Lambda or not. So if I bring up Postman, now Postman will be useful to you in this module as well, because we're not going to be developing any front end for any applications that we develop. We'll only be developing the back end or the web API part of it, I suppose. And how are we going to test that back end? Well, Postman would seem to be a good choice. And with Postman, I don't know how much you've used it. I know we used it a little bit in the web app dev module last year, but it's quite nice, really. You can do things like create collections. So if you've got if you want to have a number of, there are a number of requests types that you send to your backend, rather than having to re-enter them over and over again, you can generate a collection and configure that collection just to make life a little bit easier. And that's essentially what I've done here. How do I create a collection? I think it's just this one here. Is that the option? Sorry, no, it's just stuff popping up in front of me as usual. No, I'm just going to skip over the creating of a collection, I think. Just give me 1 second. No, okay. Let's just move on. I've created a collection here called this one. Now, in a collection, you can kind of configure the collection, I suppose. In this case, because I'm using this collection to invoke function URLs, and in particular, I'm going to be invoking a protected function URL, then I need to provide access keys to the Postman application itself, and it'll take care of doing the authentication, generating the appropriate authentication headers, etc. So let's see. Something in my way here now, sorry. I'll get rid of that. Okay, let's go back to here. So I've got this collection and I want to configure the collection. And I know in this collection, I'm going to be sending some requests that need to include authentication. So if I click on the authentication tab, there are a number of authentication types supported by Postman, and I know you've seen this last year. And if we just select the drop-down menu, do we have a drop-down menu? Right, authentication type. You've seen some of these from last year. I think last year you used the bearer token authentication model. Well, one of the, or maybe it might have been JWT bearer authentication model. Well, one of the options is at the very bottom here is AWS. It's at the very bottom, I think. There you go, AWS signature. So it's the AWS SigV4 authentication model, and that's the model that I want to use for this particular HTTP request, because that's what that's what the server side requires. Now, when you select that authentication type, it means that you have to provide an access key and a secret access key with the to Postman. And you can do it a number of ways, but one of the best ways of doing it, I think, most useful ways, is to provide them as variables. So if I click on the variables tab here, this essentially allows you to declare, surprise, surprise, variables, and variables can be for any purpose. In this case, my variables contain AWS access keys, and I've declared 2 variables. You can call the variables anything, they're not prescribed. So I've declared 2 variables and they contain my access keys. That's fine. That's at the collection level. So I'm configuring my collection. Within a collection, then you can generate a number of requests. So this is my collection and these are the requests, and it's easy to generate more requests. So if I just select this request here, it's a GET request. Now I need to provide a URL. The URL is the one that was generated by my CDK. So if I put in the URL from VS Code in there, and I need to also complete the authentication part of this request. So if I go into that tab, because I've selected AWS signature authentication at the collection level, then that is applied to any request within this collection. And this, I'm currently looking at a particular request within that collection. So I'm inheriting that authentication type. So it's telling me here, this is the authentication option that you chose at the collection level. And when you do that, then it's asking you to provide values for these two parameters, if you like. Now, I want to use the value that I want to assign to those parameters. I want them to get them from the variables that I defined at the collection level. And that's what I'm doing here. You use this syntax, a double curly brace, the name of the variable, and a closing curly brace. So this is essentially a variable reference, and the variable is defined at the collection level. Similarly, for the secret key, I'm referring to the variable that I defined up at the collection level. So I have my URL, I have my access keys. I'm using this form of authentication. And as I said, when I click send here, Postman will take care of generating the appropriate HTTP headers. And it also, I think, generates a query string, an encrypted query string. And those are expected by AWS Lambda service at the other end. And it unpacks the request and checks the authentication and either allows the Lambda function to be invoked or not. So if we press send, then it looks like it succeeded, because this is the message that was returned by my Lambda function. So the authentication worked. And if I try and send, let's say, if I go back to my keys and I just mess up here, if I just change that. And when you do make changes, always remember to do the save, which is something that I wasn't doing originally. There it is in front of me. I think that has saved it. If I now try and resend the request, it shouldn't work. Yeah, so I'm getting an error back. So this error is generated by the AWS service itself, because the authentication has failed. So that seemed to work, the generating the URL and also making it private. But at a kind of high level, we're demonstrating Lambda functions, which is a serverless compute option. Now, Lambda isn't doing anything terribly interesting, and we're invoking it synchronously via either the CLI or via URL, if the URL is available to us. That's the synchronous model. The asynchronous model I'm just going to talk about, but we won't demonstrate it because it's a bit more complex in terms of setting it up. The asynchronous model is relevant if you have, if you want to associate an S3 event as being the event source for triggering your Lambda, or if you're using a simple notification service, if you want that to trigger a Lambda and some other options as well. Like if we demonstrate the S3 one might be the easiest one to explain. So the idea is, and I think I've probably mentioned this already now, but sorry, no, it's just trying to move something out of my way here on the screen. The idea is somehow, some way you have access to an S3 bucket, and let's say we add an object to that bucket. We have our Lambda function over here, and we've configured the Lambda via our CDK in our case, such that we want this Lambda to be invoked whenever a new object is added to the bucket. When that eventually gets deployed, what the AWS service does is it generates a queue, and when the event occurs within the S3 bucket, the S3 service will communicate that event to the AWS service. The AWS service will know that event is associated with this Lambda, and it will add the event itself to this queue. And there may be many of them, you know. So the events themselves are queued up in this structure here, which is all created behind the scenes for you by the AWS service as a result of our CDK code. And it invokes the Lambda then. It triggers, the AWS service triggers the Lambda to go and retrieve whatever events are in this queue. So what it actually will receive is a batch, or it could be a batch of just one, but it receives a batch of events that are linked to the S3 bucket, and it just processes them. And we will do that a little bit later on. But how is this model asynchronous? It's asynchronous because this is my client way over here, and my client is not waiting for the Lambda function to process the events. All the client is doing is putting an object into the bucket, and then it's finished as far as it's concerned. The triggering of the Lambda happens asynchronously behind the scenes between the S3 service and the AWS Lambda service via this kind of queuing mechanism that's managed for you by AWS itself. And at the risk of repeating myself, in your CDK code, all you've got to provision is the S3 bucket, the Lambda function, and express, and we'll see how, express the fact that you want this Lambda to be triggered or invoked as a result of a new object being added to the S3 bucket. Express that in 2 lines of code, and the rest then is taken care of for you. But either way, it's an example of this asynchronous model, and I've explained why it's asynchronous. It's asynchronous relative to the client on the extreme left. So the Lambda service up here, I'm saying the Lambda service places the events in a queue. The Lambda service, if for whatever reason, so it will invoke, it will trigger your Lambda, and the Lambda will process a batch of events from the queue. If for whatever reason the Lambda crashes, we needn't get into the details of why, then if the Lambda function crashes, then the Lambda service will actually retry the invocation, or it will re-invoke the Lambda again to try and complete the processing, and it does that 3 times. I think it's pre-configured to retry it 3 times. Eventually, it gives up on it, and we kind of have to deal with the consequences programmatically some way. But the Lambda service will take care of re-invoking your Lambda on a number of occasions to complete the processing. And because of that, you've got to make sure that I'm saying here that your Lambda implementation is idempotent, because what might happen is the Lambda gets invoked with a batch of 10 events. It processes the first 5 and then crashes, which means the Lambda service will re-invoke your Lambda function, gives it the batch of 10 again. Now you've got to make sure, because it's already processed the first 5, whatever the nature of that processing is, it needs to be idempotent, because it is actually going to process the first 5 all over again. So you've got to be aware of that, is all I'm saying. I'm saying here it does 3 retries using what's called a an exponential back-off algorithm. All I mean by that is that the second execution, it will delay the second invocation for a period, let's say 3 seconds. If the Lambda still crashes, then the Lambda service will delay for double that, 6 seconds, and then tries again. If it still crashes on this second occasion, it will wait for double the delay time, which we're now up to 12 seconds, and then invoke it again. And now we've had 3 retries. At that stage, it gives up. And we can talk some other time about how we clean up all of this stuff. But the Lambda service takes care of retrying your Lambda function on a number of occasions in case of failure. Why would we take this approach at all? Like, you might ask, why not have a Lambda here so that the client sends the object to your Lambda function, your Lambda function processes it, and then puts it into the bucket? That would be a synchronous approach, because now our client, because it's invoking the Lambda directly, our client is waiting for the Lambda to do the processing and put it into the bucket. Whereas in the asynchronous model, all it's doing is just put the object into the bucket and it's finished. And the reason you might take this asynchronous approach is because, well, maybe the client doesn't really need to care, doesn't care about whether the processing has been completed or not. All it cares about is, has the object been added to the bucket? The client doesn't have to wait for all the processing to happen. And that means our client-side application there's a faster response to the end user as a result. Okay, all of the processing hasn't been completed, so the end user can say, just because they got a response back, that all of the processing has been completed. But there are occasions when this asynchronous model is suitable. So we've got the synchronous model, we've got the asynchronous model, and the third option is this event source mapping model, which is kind of odd, kind of an odd one out, but it's there for technical reasons. We don't need to, nor have I studied in detail the technical reasons for it. But the way this third model is implemented, and it applies if you're using what are called DynamoDB streams. So the idea here is your client is, let's say, updating this DynamoDB database, which it's just an ordinary database as far as we're concerned. It's adding records, it's modifying records. And we want a particular Lambda function to carry out some processing as a result of some change to the database. Again, we don't have to go into detail of what the nature of the processing is, but we want to trigger a piece of functionality every time there is a change in my database state, as in new record added, record has been deleted, record has been updated. So that's the event that I want to trigger my Lambda function, the change within my Dynamo database. And so the way it works, again, from a CDK point of view, you provision the Lambda function, you provision the DynamoDB database, and you express the fact that you want this Lambda to be triggered by the state change in the database. And then the AWS service sets up this kind of infrastructure. And the way it works in this case is it works on a polling basis. The AWS service periodically asks the database, have you experienced a state change since I polled you the previous time? And there may be a number of state changes between 2 consecutive pollings. So the AWS service does that polling for you. If there have been a number of state changes, by the way, every time there is a state change in my DynamoDB database, that state change is logged internally by DynamoDB. And we refer to that log as a stream. And so when the AWS service polls the DynamoDB database, it essentially gives that stream of logs as the response. That stream is put into this intermediate queue, and yet again, the Lambda service is provided with the contents of that queue as a batch of events, and it processes them again. But the key point here is that the AWS service is polling my event source for events, whereas in the asynchronous model, if I just quickly go back to it, in this model, the event source is telling the AWS service about the events. It's providing the events to it. And okay, the AWS service puts them into the queue. So there's a different kind of invocation sequence going on between this asynchronous model and the event sourcing model. This event sourcing idea is also used by SQS, which is a service that we'll use later on. It's also used by Kinesis streams, which we won't use. So we will see later on an example of where we can set up a Lambda that's triggered by a DynamoDB database state change. Okay, that's kind of a lot of talk really, but there you go. In next week's lab, you will go through the process of writing a CDK app that creates a couple of Lambdas, and some of those Lambdas will actually talk to a DynamoDB database. I will kind of formally talk about DynamoDB in next week's lecture, but you know, a database is a database is a database. And we'll also set up some URLs for our Lambda functions so that we can invoke them either from a browser or using Postman. As regards this week's lab, it didn't really work out the way I would have wanted it, obviously, because we didn't get past that 502 bad gateway error. But from CDK's point of view, it did everything we wanted it to. It created all of the infrastructure. The lab fell down because the application that I'm running on that infrastructure was a bit flaky. I think the problem actually has got to do with the installing of Node inside the EC2 instance. That's where I am at this stage, but I'm not going to spend any more time trying to debug it. As far as I'm concerned, I'm happy if you have got to the stage where you've deployed the stack and okay, you've gotten that 502 error, and that proves that the stack is fully deployed, albeit not functioning properly. The last thing I will say to you is make sure that you destroy your CDK stack straight away, really, once you've achieved that, once you've achieved the deployment of it. Destroy it straight away, because it is consuming or it is costing you, even though it's not being used. Okay, I'm going to leave it at that for now, and I'll talk to you next week. Thanks a lot.